Okay, so welcome to the 10th live session of the NPTEL course Chemical Process Intensification. If you have any doubt, feel free to chip in. Otherwise, I will just go on discussing what has been discussed in this week content of the course. This week was heavily focused on the process intensification for the systems which involve extraction. And so we will first start with what is extraction. As you know, the extraction, basically the solid liquid or liquid liquid or gas liquid system, all of this system or the extraction, they kind of utilize the principle of extraction. The extraction of active chemical compounds from the natural products is one of the important research area for the pharmaceutical and chemical industries. So it all starts from, if you take the example of pharmaceutical and chemical industries, if you want to enrich a particular component, you can do that by distillation and all, but if you want to extract a specific solute from the mixture, or from, let us say for example, if you're interested in some kind of an Ayurvedic component from a particular herb or plant, then you need to extract from it. So that extraction would basically be most likely be the solid liquid extraction system. So extractions are a method to separate a desired substance when it is mixed with others. So here, for example, your desired molecule or the desired substance is that Ayurvedic molecule which has that molecule which has some benefits, and you want to extract that. So you will basically extract that. So that is your desired substance, and it is mixed with the other components like cellulose and everything which you cannot digest. So you need to extract the your desired substance from the other bulk matrix which is of less desire. So yeah, the mixture is then brought into contact with the solvent in which the substance of interest is soluble, but the other substances present are insoluble. Insoluble. Now the extractions use two immiscible phases. These are the phases that do not mix like oil and water to separate the substance from one phase into the another. For example, in the liquid extraction, your solvent or the light phase could be, for example, like paraffin, and then you will mix with this light phase, the solvent, with the feed solution, which will be a heavy phase, that will be a mixture of solutes. So then you will basically extract the paraffin from the feed solution by after mixing or making an emulsion out of them, a temporary emulsion, then letting it to settle down to basically undergo phase separation. So then you will basically your extract is then basically your solvent with the solutes, with the desired solutes. Those are called as extract, and the raffinate is what the leftover mixture without the solutes, but it will contain some solutes with the non-extracted solutes. But yeah, after the phase separation, the extract will the two phases will be called as extract and raffinate, The extract is the phase which contains your desired solutes which has been diffused into it, and the raffinate is the one which is no longer heavily concentrated with the desired material. Similarly, in case of making tea, you boil the tea leaves in water to extract the tannins, theobromine, polyphenols, and caffeine out of the solid tea leaves and into the liquid water to make the tea. That is basically one of the example of solid liquid extraction process, where you will extract your desired components, the components of interest such as the caffeine from the tea leaves into the water to make the tea. Now let us discuss the applications of the extraction. So one of the few examples, we will just discuss a list of applications for the extraction processes. So one such example is for the, largely for the pharmaceutical industry, chemical industry, perfume manufacturing, or pesticide industry. They basically revolve around the extraction process. So because they deal with the recovery of active components from plants and vegetable seeds. For example, for the perfume manufacturing, you might need to recover or extract some kind of vanilla flavor from the plants. So then you need to perform extraction. Or similarly, as discussed in the pharmaceutical industry, you might be interested in some kind of a molecule which has some benefits to the body, human body, and that might be found in some kind of a herb. So then you need to extract those compounds from the herb to basically manufacture your tablets or pills for the human consumption. Now another example is the extraction from the, basically, we cook food. So because the vegetable materials contain only a small amount of active solute, but in most cases high value of active compounds justifies the development of high performance separation processes. Another example is the supercritical carbon dioxide. The utilization of supercritical carbon dioxide for the extraction of caffeine from coffee, one of the example. Another example of using supercritical carbon dioxide for the extraction process is to extract the oil from nutmeg. And another final example is the extraction of nicotine from tobacco using the supercritical carbon dioxide. Another example is the separation of carbon dioxide from solute, for example, in the carbon sequestration, and it is often possible by simply reducing the extract pressure. So as you reduce the pressure, its solubility will increase and you will basically separate the carbon dioxide from the solute very easily. Another application of extraction processes is the extraction of nitrobenzene after the reaction of nitric acid with toluene in presence of sulfuric acid. So this reaction of nitric acid with toluene in presence of sulfuric acid will give out the product of nitrobenzene with other undesired quantities. So you need to then extract the quantity of interest, here being nitrobenzene. So you need to extract that. Another example of application is the extraction of methyl acrylate from the organic solution with perchloroethylene. Another example is the extraction of benzyl alcohol from a salt solution with toluene. Another example is the removal of sulfuric acid from liquid petroleum gas using MDEA, which stands for 3,4 methylene dioxy and ethyl amphetamine. Another example of the application includes the extraction of caprolactam from ammonium sulfate solution with benzene. Another example includes the extraction of acrylic acid from wastewater with butanol. Another example of the application of the extraction processes include the removal of residual alkalis from the dichlorohydrazobenzene with water. Another example includes the extraction of methanol from liquid petroleum gas with water. Another example includes the extraction of chloroacetic acid from the methyl chloroacetate with water. So now, as we have discussed the applications of extraction, now let us move on to the methods that has been used conventionally for the extraction processes. Then we will further discuss that how we can modify the conventional methods for the extraction to perform process intensification, basically utilizing some another kind of technology which will help us to intensify the conventional method for the extraction process. So traditionally, different mechanical and chemical processes has been utilized for the conventional method as a conventional method for extraction process. Those traditional methods or traditional processes include a solvent extraction, steam distillation, high hydrostatic pressure extraction, pulse electric field process, high pressure process, ultrasound assisted extraction, and further there are other examples too. Now, as for the selection criteria, so all of these methods which I have just listed, so how will you select which one works for you, which method will work for you? So the selection criteria is to basically, or I should say, the objective function is to maximize the yield and also maximize the purity of the active components in the extract phase. So that is how you will do that. So the selection of the methods to extract active components with maximum yield and highest purity, that is your goal, and this will depend on the nature of compounds, thermal stability, and nature of raw material to be processed. So you need to first basically the goal is to maximize the yield and highest purity, and that will depend on the nature of compounds, thermal stability, and nature of raw material to be processed. And all of these three depend on the mixture solution. Now the traditional techniques have a lot of limitations. So we will first discuss what are those limitations, and then we will go to the introduction of what are the other methods or what are the other solutions for these limitations to basically intensify the extraction process by inculcating other different technology into the conventional or traditional extraction processes. So let us discuss the limitations. So the limitations, the conventional techniques are often limited by the mass transfer resistances due to the involvement of more than one phase in the system. So because the extraction processes are basically multi-phase system, and the simplest multi-phase system is a two-phase system, which is more than a single phase system. So as the different phases are getting involved, there will be an interfacial mass transfer involvement. An interfacial mass transfer generally has a lot of resistance. So those conventional methods are often challenged by the interfacial mass transfer resistances, and if you are able to successfully overcome it, then you will have an intensified process. So one of the major limitation is the interfacial mass transfer resistance that is encountered in the multi-phase extraction systems. Now these methods are time consuming and may require fairly long time, lower yields depending on the diffusion rates of the solvents through the tortuous path of the material. Okay, so another limitations is that these methods are time consuming. The extraction methods are very time consuming and may require fairly long time, and yeah, so therefore, and depending upon the diffusion coefficients, they will be having very lower yields. So yeah, in heat sensitive active compounds, extraction carried out at higher temperature may damage the quality of the extract. So if your extraction also involves heating, then your heat sensitive active compounds may get destroyed, or your quality will decrease. And also in certain cases, the active molecules may be destroyed due to the use of severe pressure also. So for example, in this use of very high temperature in tea, and extremely high pressure can destroy certain beneficial compounds or beneficial active compounds. Mechanical processes presents poor efficiency and low yield. So if you stick to purely physical and mechanical processes, you will often observe that your extraction processes will be having very poor efficiency and extremely low yield. While the chemical extraction methods involve use of large quantity of organic solvents, which are harmful to human and environment. Conventional methods exhibit lower efficiency due to decreased molecular affinity between solvent and solute, and high energy consumption is also one of the notable disadvantage of the conventional extraction processes. So these are the limitations of the conventional or traditional techniques of extraction, that they generally have very low efficiency and may also destroy the active compounds when high temperature and pressure are used, and often high energy consumption is also noted. And if you stick to purely mechanical or physical extraction process, then your yield will be very low and you will need a lot of very high contact time, up to days, which you don't want to basically have. So that's why you need intensification. So that's why you need intensification. Now we shall discuss why intensification is required. So yeah, why intensification is required for the traditional or conventional methods of extraction. The government health and environmental regulatory requirements on the use of organic solvents have encouraged active research on clean extraction techniques. So, because of the environmental constraint, health constraint, and government regulatory requirements, we need to perform extraction in a much cleaner fashion, and that would often require to not use highly toxic chemical components. So you need to devise an new, novel, and intensified way to perform extraction without harming the environment, and also coming in under the government's health regulatory requirements. So that is why you need to perform intensification of extraction. Another reason for the intensification of extraction processes is the need for effective extraction techniques for the active components from plants without any loss of activity and high purity. So often in the conventional extraction processes, if there is an involvement of high temperature, high pressure, or a very extremely toxic and reactive solvent, this would often lead to the loss of the activity for the beneficial active component from the plants while the process of extraction undergoes. So that will lose the entire purpose of it. So you need to, that is why you need to use some, or to develop a novel kind of extraction process with the intensified approach. Another reason for the requirement of intensification is that the confines of the conventional techniques make obstinate for search for a new technique which are equally competent and at the same time economically viable. So basically, these are the reason for the performance of intensification. Now let us go and look at intensified approach for the extraction, which is the electrohydrodynamic EHD technique for the extraction. So this is basically one of the way to intensify the conventional extraction processes. So the electrohydrodynamic technique has received has lately received a considerable attention as an important non-thermal method that is used for food processing especially, and it is a complementary process for cellulose extraction from bagasse. Bagasse is the leftover part of the sugar cane after the extraction of sucrose from the sugar cane. Now, the sugarcane bagasse has the largest cellulosic fibrous agro-industrial residue left over after the sugar extraction from the sugarcane, and is mainly considered as a waste which affects the environment. So, how can we utilize the bagasse? So, the main component of the bagasse are about 40 to 50% of semicrystalline cellulose, 20 to 35% of amorphous hemicellulose, and 10 to 14% of lignin. So the cellulose can be easily extracted from sugarcane bagasse. So here the idea is to extract the cellulose for the paper making, and the cellulose can be easily extracted from the sugarcane bagasse by acid hydrolysis followed by the alkaline pulping process. The hydrolysis and alkaline pulping partly eliminates the lignin and hemicellulose via breaking them into soluble units of low molecular weight. So this is basically an introduction for the electrohydrodynamic technique for the extraction, where basically it is mainly used as a complementary process for the cellulose extraction from bagasse. So how does the electrohydrodynamic technique electrohydrodynamic technique for extraction works? The electrohydrodynamic technique for is an important non-thermal method through which an high voltage electric field generates an electric wind by gaseous ions, and this ionic wind as an ion drag phenomenon is generated when the charged ions and non-charged molecules collide with each other. Now, during electrohydrodynamic process, the charges interact with gas, dry matter and liquid water of the food under the effect of a strong electric field. So this is how the electrohydrodynamic extraction works. So it is a non-thermal method, and a high voltage electric field generates an electric wind by gaseous ion. So let us say if you have a gas liquid system, now then ionic wind as an ion drag phenomenon is generated when the charged ions and non-charged molecules collide with each other. Now as the electric wind interacts with the gas, dry matter and liquid water of the food, the extraction will continue. Now the low energy consumption and high product quality are two issues that are compiled with electrohydrodynamics. It is suitable especially for the thermally insensitive materials. So the electrohydrodynamic technique for extraction is especially suitable for the thermally sensitive materials. Now the electrohydrodynamic system may consist of a wood framework and a needle bling electrode system a fixed grounded plate made from copper and a set of needles made from steel is fixed on a plexiglass plate and can be used as the electrode system. The electrohydrodynamic system can be equipped with a high voltage power supply. The corona discharge is generated by connecting the needle electrode to the DC high voltage. So this was demonstrated by the paper by Ahmadzadeh in 2018 in Carbohydrate Polymer 188th issue. So the bagasse or the bagasse in the samples first defat using Soxhlet apparatus with hexanol for 6 hours, which is similarly performed for both EHD treated and untreated samples. Then a 3-step process is described to extract the cellulose fiber from the sugarcane bagasse by Ahmadzadeh and others in 2018. So what are these 3-step process? The 3-step process is that the electrohydrodynamic treated mixture of fibers in 0.78% of sodium chloride solution is boiled under the reflux of the pH of about 4 or 3 at pH 4 for about 3 hours to remove the lignin. So the first process is to remove the lignin by the treating of the electrohydrodynamic treated mixture of fiber in 0.78% of sodium chloride solution and then boiling it for 3 hours at pH of 4. So this will remove the lignin, which is one of the difficult part because lignin is quite strong and stretchy. The obtained material is then treated by electrohydrodynamics after the mixing with 5 weight percent of sodium sulfide solution, and then the whole mixture is boiled for 3 hours. The bleached fibers are then washed with distilled water to attain a neutral pH. And then the third step is to subsequently obtain the fiber and boil it in 17.5 weight by volume percent sodium hydroxide solution for 3 hours for hemicellulose hydrolysis. Finally, the insoluble residue is filtered, washed until the filtrate was neutral to eliminate the excess of soda, and dried at 80 degrees Celsius until reaching to a constant weight. The treatment under a high voltage electric field was performed for 2 hours at the beginning of each step. So this demonstrates the using of electrohydrodynamic assisted extraction, and this specifically demonstrates for the extraction of cellulose from the bagasse of sugarcane plants after all of the sucrose and sugars have been removed. So yeah, let us now discuss ultrasound assisted extraction. So the as discussed in the previous weeks too, that the use of ultrasound results in the formation of cavity, or basically the spontaneous evaporation of fluids at a localized space to basically that is cavitation. So the use of ultrasound results in cavitation, which is commonly described as the formation, growth, and collapse of gas vapor filled bubbles in a liquid. Sonochemistry specifically involves cavitation induced by pressure fluctuation generated by ultrasound waves in a liquid medium. Now, the ultrasound can be effectively used to increase the yield and rate of mass transfer in several solid liquid extraction processes. The mechanism of intensification of extraction process has been attributed to the cavitation phenomena, resulting in intense turbulence and liquid circulation currents in the system. In the case of extraction of natural products, ultrasound based cavitation has been reported successfully for different applications. For example, in the extraction of vanillin, almond oils, vanilla, almond oils, herbal extract from fennel hops, marigold, mint, ginseng saponins, ginger, soy protein, soy isoflavones, carnosic acid from rosemary, polyphenols, amino acid, and caffeine from green tea, pyrethrines from flowers, etc. So how does the ultrasound assisted extraction actually work? So what is the mechanism of ultrasound assisted extraction? So the mechanism, let us discuss. The intensification of extraction efficacy due to the propagation of ultrasound pressure wave through the solvent and resulting cavitation phenomena. So yeah, the controlling mechanism of ultrasound assisted extraction is generally attributed to mechanical cavitation and thermal effects, which can this can result in the disruption of cell wall particle size reduction and enhanced mass transfer across cell membranes. So let us say if you want to extract a particular protein or compound from the cell inside the cell, and you need to break the cell because diffusing that bigger protein chains from the cell membranes, which has very small walls, you cannot achieve that, so you need to break the cell. Then here the ultrasound assisted extraction can help to break the cells in bulk and then extract the particular protein of or compound of interest. So first you will break the cell wall due to cavitation, and then the diffusion of the solvent into the cell structure will then achieve the extraction of the solute. So the implosion of the cavitation bubbles, so the cavitation bubbles will be generated by the ultrasound, and then after generation very quickly they will implode. So the implosion of the cavitation bubbles will generate microturbulence, high velocity interparticle collision, and perturbation in microporous particles of the biomass. So all of these three, the microturbulence, high velocity interparticle collision, and perturbation in microporous particles of the biomass due to the implosion of cavitation bubble, all of these three will accelerate the eddy diffusion and internal diffusion. And it has been reported that the microfractures that appeared in the particles after the application of ultrasound and the surface morphology of the particles changed and giving more porous nature and enhancing the mass transfer of the extraction. For example, extraction of oil from soybean flakes, autoclaved almond powder, and extraction of ginger oils from ginger. Now, some of the I will just go and discuss some representative examples of process intensification levels using ultrasound assisted extraction. So, for example, the material that is extracted from is the polyphenols from the orange peel, and the equipment that is used for the extraction of polyphenols from the orange peel is basically an ultrasonic bath that operates at about 25 kilohertz. And what are the remarks or the results that has been obtained is that the total phenolic content obtained by the ultrasound assisted extraction during 15 minutes was significantly higher than the Soxhlet extraction during the 60 minutes. So yeah, you can see that just for performing in the 15 minutes you can achieve the same efficiency as that of the Soxhlet extraction apparatus that was operated for 60 minutes. So that is about reduction of almost 45 minutes. Another example is the extraction of biophenols from olive leaves. by basically using an probe type ultrasonic equipment that is operated at 25 kilohertz. The ultrasound assisted extraction for 25 minutes gave the same yield as the 24-hour conventional method. So this is a very significant reduction. Another example is the extraction of natural pigments from the rhizomes of curcuma longa leaves, and this was done by using an ultrasonic bath that was operated at 35 kilohertz. The yield of ultrasound assisted extraction was 3 times higher than the traditional method. So that is another, so 3 times higher. And another example is the extraction of capsaicinoids from the capsicum frutescens, and the equipment used was the ultrasonic bath that was operated for 35 kilohertz. In 3 hours, the ultrasonic assisted extraction gave about 87.4% yield as compared to 79.4% for the industrial hot maceration process for about 15 hours. So you save 12 hours of time, and that too you have much higher yield than that of the conventional means. Another example is the extraction of soy isoflavones from soybeans, and in that the equipment that was used was a probe type ultrasonic machine that was operated at 24 kilohertz. So for different solvent, isoflavone yields obtained with the ultrasound assisted extraction were about 0 to 15 about 15% higher than those with the stirring and mixing. So yeah, about 10 to 15% of increase. So another example is the extraction of hemicellulose from the wheat bran, and the equipment that was used for this was for the extraction of hemicellulose was the probe type ultrasonic equipment that was operated at 20 kilohertz, and the total extraction time was shortened from 60 minutes to for the conventional extraction to 5 minutes of ultrasound assisted extraction, with about 60% of reduction in the consumption of sodium hydroxide. Another example is the extraction of madder, which is basically Rubia tinctorum root dyes. So the equipment that was used for this was the ultrasonic bath that was operated at 25 kilohertz, and the effect was that the ultrasonic process reduced the extraction time from 18 minutes to 1 hour in the conventional process, and the energy cost with a better yield. Another example is the extraction of rutin and quercetin from the Euonymus alatus seed, which was done by using an ultrasonic bath that was operated for about 50 kilohertz. And there was a significant 4-fold reduction in the extraction time and improvement in yield. Another example is the extraction of carotenoids from the citrus peel by using the ultrasonic probe system operating at 21 to 25 kilohertz. The extraction yield increased almost 3 times that of the conventional extraction for the particle sizes greater than 0.28 mm. So basically the possible the combination and other approaches for the intensification of extraction operation. So it is not that you can just only combine with the electrohydrodynamic or the ultrasound assisted extraction. You can also combine the extraction with other possible approaches. So let us discuss that. So the ultrasound assisted extraction can be conveniently coupled with other extraction techniques such as supercritical fluid extraction, microwave assisted extraction, vacuum distillation, and enzymatic treatment. The combined approach possibly results in the overall increase in the efficacy of the operation and a significant intensification of the extraction operation. Now, the another example is the combination of microwaves with the ultrasound waves. This would provide very extremely high amounts of momentum and energy to rupture the plant cell and elute the active compounds to the extraction solvent. Now, as a result, the extraction will proceed with a shorter extraction time and lower solvent consumption. So this combination of microwaves with ultrasound wave will result in the extraction procedure to proceed with shorter extraction time and lower solvent consumption. Now, ultrasonically assisted extraction can also be coupled with vacuum distillation in order to extract and subsequently concentrate the aroma compounds from natural source of herbs. It may be beneficial results of extraction based on the continuous solvent circulation in a dynamic system with ultrasound. The ultrasound assisted dynamic extraction may result in the highest yield because the extraction proceeds all the time with the flowing solvent, having therefore a better mass transfer and better contact between solvent and solid. The combination of ultrasound and enzyme treatment may increase extraction yield with short treatment time, so therefore more research is required. Now let us discuss what are the factors that influence the extraction process. So the factors that influence the extraction process include the type of stage configuration, desired degree of recovery of one or more solutes, degree of separation of the feed, choice of liquid solvents, operating temperature and pressure, number of equilibrium stages, emulsification, interfacial tension, phase density difference, type of extractor, extractor size, and horsepower requirement. The mixing is the one of the main backbone to intensify the efficiency of the extraction, where back mixing is not preferred. So now let us talk on another intensified approach for the extraction process, which is the supercritical extraction process. So, as the name suggests, supercritical extraction process is basically where your solvent will be a supercritical fluid, and the separation of one component, the extractant, from the another, which is the matrix, using supercritical fluid as the extracting solvent, is called as the supercritical extraction. And what is the motivation for supercritical extraction? Because the intensification of separation technology with fluids at high pressure are essentially vital to get new natural products. So this is one of the driving force, one of the main necessities that give birth to the supercritical extraction. Now, among the intensified extraction techniques, the supercritical fluid technology offers products free of residual solvent and that typically present high quality when compared to the products obtained by conventional techniques. The extracts of bioactive compounds can be obtained by the extraction of solid matrices such as the leaves, seeds, pulps, etc., or by the extraction or fractionation of the liquid mixtures, which is aqueous solution, fish oil, microalgae oils, vegetable oil, deodorized distillates, etc. At high pressures which are near or above the critical point, now which often involves the pressure and temperature, the solvent density increases drastically, and this is the most important parameter associated to the solvent extraction. So yeah, supercritical extraction basically involves the separation of one component, the extractant, from the another using supercritical fluid as the extracting solvent. Now it is a diffusion based process in which the solvent is required to diffuse into the matrix and the extracted material to diffuse out of the matrix into the solvent. So the diffusivities are much faster in the supercritical fluids than in liquids, and therefore extraction can occur faster. So what is the most important fluid or most common fluid used in the supercritical extraction? It is actually the carbon dioxide. So carbon dioxide is the most important fluid in the supercritical fluid technology in the extraction, separation, fractionation, micronization and encapsulation processes. So carbon dioxide is applied to obtain extract concentrate with bioactive compounds for food, pharmaceutical and cosmetic application. Carbon dioxide is actually a non-toxic substance which acts as a solvent, co-solvent or anti-solvent. So it can perform the extraction process at extremely high pressure, and also for it can be used for the extraction of bioactive compounds. So the carbon dioxide has a critical temperature near to room temperature, contributing to the operating condition, pressure and temperature, to extract the thermolabile substance such as the bioactive compounds. So for example, for the extraction of the bioactive compounds which need to stay on the room temperature, not to extremely low, not to the extremely high. So such temperature and pressure condition can be achieved by the carbon dioxide as its supercritical state. In its supercritical state. Now it is non-polar, and to enlarge the application spectrum to extract bioactive compounds, ethanol, water or both are usually used as co-solvents. So it is a non-polar, and it is the carbon dioxide is non-polar, and to enlarge the application spectrum to extract bioactive compounds, ethanol or both are usually used as co-solvents. The carbon dioxide acts as a co-solvent when in the mixture it is used more than 60% of ethanol or water, and as an anti-solvent when the solute extract is not soluble in the carbon dioxide during the depressurizing step. So when it is used more than 60% in the combination of more than 60% of ethanol or water, it becomes co-solvent, and it is works as an anti-solvent when the solute extract is not soluble in the carbon dioxide during the depressurizing step. So under the high pressure it will be soluble, but under depressurizing step it will not be soluble. So thermodynamic phase equilibrium determines the limit for the mass transfer among different phases. The triple point of the carbon dioxide is at pressure of 5.18 bar and a temperature of minus 56.57 degrees Celsius, and the critical point is at the pressure of 73.7 bar and the temperature of 31 degrees Celsius or 304.15 kelvins. So when the substance is in the state above the critical temperature and critical pressure, it is called as supercritical fluid. Now let us discuss the solvating power of a supercritical solvent. The density is the most important thermodynamic property to define the solvating power of a supercritical solvent at high pressures. Now increasing the density of the solvent increases its solvating power. As we know, for carbon dioxide, the critical point is at the pressure of 73.7 bar and at the temperature of 304.15 Kelvin or 31 degrees Celsius. It makes carbon dioxide as the most applied solvent to extract thermosensible substances. Because of the temperature is just 31 degrees Celsius. So yeah, if there is a thermosensible substance, so 31 degrees Celsius is very near to the room temperature. So yeah, that is why it is most applied solvent to extract thermosensible substances. So what is the general process step for supercritical fluid extraction? Generally, the supercritical fluid extraction applied to a natural solid matrix consists of 3 steps: the system supply of solvent co-solvent, the extraction unit, and the extract separation system for solvent and co-solvent. So what is the procedure? The supercritical solvent continuously flows through a fixed bed of solid particles and dissolves the extractable components of the solid. The solvent is fed into the extractor and evenly distributed at the inlet of the fixed bed. The system solvent and the soluble components leave the extractor and feed the precipitator separator, where the solvent products are separated by the expansion by the depressurizing. Since at low pressures the density of the solvent sharply decreases, therefore it decreases the solubilizing power of the solvent as well and the product precipitate. Choice of operating condition. The choice of the operating condition pressure and temperature is a determining factor that contributes to a maximization of the extract solubility in the supercritical solvent and consequently the extraction yields. Increasing the density of the supercritical fluid, the insolubility of the solvent maximizes. The solubility increasing can also occur when co-solvent is added, which changes the solvent power, and in this way a new solvent is a mixture. So now let us discuss the design aspect. To design a high pressure fluid extraction process of valuable components from a new natural solid matrices, it is necessary to define the size of the extraction unit, and some important parameters have to be determined to obtain the optimum process condition for each application. Now, what are the most important design parameters? The most important design parameters and among the variables that determine the processes are the operating condition, which is pressure and temperature, the amount of solvent that is required, the condition of the solvent removal from the extract, such as the precipitation, and pre-treatment of the solid matrix and other mass transfer parameters. What are the variables that affect on the mass transfer behavior? Mass transfer at processes at high pressure are related to the configuration of the bed, particle size, height and diameter, preparation of the raw material, solvent use. So what are the high pressure CO2 properties? Because carbon dioxide will be in a supercritical state, will be in very extremely high pressure, 23 bars. So what are the properties of high pressure carbon dioxide? The properties of the high pressure carbon dioxide is that the viscosity decreases, diffusivity increases, and thermal conductivity increases with the decreasement in pressure at the high pressure stage. And the dielectric constant is basically that the carbon dioxide is A4 in nature, and this is what increases to the carbon dioxide as a supercritical solvent. So now let us discuss what are the applications for the supercritical extraction. One of the example is the essential oil extraction. Isolation of essential oil such as the other oils. The use of the carbon dioxide as supercritical fluid has been considered a chemically green, unconventional extraction technique that does not alter or degrade the substances present in oils because it uses relatively low temperatures in the extraction process. So it was given by Duan and others in 2007 in their paper of comparison of essential oils of clove buds extracted with the supercritical carbon dioxide and other three traditional extraction methods. Another example is the phytosterol extraction. So phytosterols or plant sterols are non-volatile triterpenes, and the great majority of these compounds are formed by carbon with one or two carbon-carbon double bonds. These compounds have various biological activities such as lowering the total serum or plasma cholesterol levels and low density lipoprotein cholesterol levels. In addition, they have anti-tumor activities inhibiting the development of colon cancer. For the extraction of these phytosterols, the supercritical carbon dioxide has been shown to be an efficient technique for the extraction of fixed oil from vegetable matrices. So the extraction with supercritical carbon dioxide modified with water in different proportion is carried out to obtain bioactive compounds of high polarity, because carbon dioxide is a non-polar molecule and does not have power to solubilize polar substances such as in the case of phenolic compounds. So what are the factors that directly control the yield? It will be the solvent flow rate, percentage of co-solvent type, which is ethanol or water, and extraction time. So these four will directly implicate the yield of the substances at the end of the extraction process. There is another aspect. What about subcritical extraction? So supercritical versus subcritical extraction. The supercritical extraction, being a much stronger solvent than subcritical carbon dioxide, allows for faster and more complete extraction. By supercritical method, the lighter oils as well as not so desirable higher molecular weight materials such as the waxes, paraffin, lipids and resins can be extracted. These fatty waxes will then need to be removed from the extract by a process called winterization. So you can see that supercritical extraction is much better than the subcritical extraction. But still there will be an advantage. The advantage of subcritical extraction is that the advantage of subcritical over supercritical is that the extracted oil is pure, free of fats, waxes and lipids, so less amount of post-processing work will be required. The purer oil doesn't need to be further refined and can be used just as it is edible and other products. So for the supercritical extraction, while the processing might itself be an easy one, but you need to do a large amount of post-processing. So the carbon dioxide extraction is basically safer, purer and cleaner. There are a number of advantages to extracting with carbon dioxide, whether subcritically or supercritically. One is that no traces of solvent are left behind versus other methods of extraction using hydrocarbons. Carbon dioxide is not a volatile solvent, so there is no need for special safety equipment. Finally, carbon dioxide is relatively cheap and can be recovered and recycled 90% of the carbon dioxide used in each extraction. So there are some other general strategies to optimize the supercritical extraction. So to maximize the diffusion can be achieved by increasing the temperature or swelling the matrix and reducing the particle size. The matrix swelling can sometimes be increased by increasing the pressure of the solvent and by adding modifiers to the solvent. Some polymers and elastomers in particular are swelled dramatically by carbon dioxide, with diffusion being increased by several orders of magnitude in some cases. Maximizing solubility. Generally, higher pressure will increase solubility. The effect of temperature is less as close to the critical point. Increasing the temperature causes a decrease in the density and hence dissolving power. At pressures well above the critical pressure, solubility is likely to increase with temperature. Addition of low levels of modifiers such as the methanol and ethanol can also significantly increase solubility, particularly of more polar compounds. Now, optimizing the flow rate. To maximize the rate of extraction, the flow rate should be high enough for the extraction to be completely diffusion limited but wasteful of solvent. To minimize the amount of solvent used, the extraction should be completely solubility limited, but then again you would require long residence time. The flow rate must therefore be determined depending on the completing factors of time, solvent cost, capital cost of pump, heater and heat exchangers. So the optimum flow rate will probably be somewhere in the region where both solubility and diffusion are significant factors. So yeah. So that's all for today, the live session and the 10th live session for the course. If you have any doubt in the 11th week course content, so feel free to come in and discuss. So otherwise I will continue to discuss what has been discussed in the next week. So okay, thank you.